around more than 8,000, right? So he is a pioneer in the field of computer visions, right? And affective computing especially. So we are pleased to have you today, sir. So over to you, sir.
Thank you. Thank you so much for the very, very warm introduction, Dr. Deepak. And good evening, everyone. My apologies, the camera on the laptop stopped working for some reason. I have no idea. Been trying to fix it for the past few minutes, but
No
um,
problem.
I'll go directly into this. So I would be speaking for the next 50 minutes or so on some work which we have been working around in deepfake analysis. So my with my students and collaborators here in Monash University in the state of Victoria, so which is in southeast of Australia, we have been investigating essentially understanding of human behavior using sensors and algorithms. So this area is called affective computing, which essentially we would like to create systems which can sense affect in the form of perceived emotion, and then through these adaptive smart interfaces or agents react accordingly so as to increase the efficiency or productivity and safety of the user. So we use these series of sensors, different type of modalities for our research. And essentially the research is focused towards three main questions. The first is, how can we understand human behavior in real world settings? Now in real world settings, by that I mean, assume we are using a camera, then the person could be outside and it could be very sunny, or the person could be inside a room which might not be very well lit, and there can be multiple sources of illumination as well. On top of it, there would be scenarios where there is a head pose movement, that is when a camera captures the face of the individual, the face is not exactly frontal and not looking into the camera. Further, once we have developed, say, these methods, in research question 2, we are interested in using that information, using the affect for different sort of problems. So how can we understand the human behavior better using affect, and then increase the effectiveness and engagement of different applications? The third one is, once we have understood the user reaction, let's say that has improved the task which you are trying to achieve, then how can we include this in a more effective human-human or human-machine interaction? Okay. Now, what I would do is, you would be wondering that I was going to talk about deepfakes and I'm talking about effective computing, but essentially the way we are looking at deepfakes is essentially part of our research question 2. But I'll take the next few minutes just to show you some of the works which we have been doing in the past few years on these three different research problems. So here is the first one, pretty, I should say, elder old now, but what we have been interested in is understanding the overall group's mood. That is when a viewer looks at the whole group, how do they analyze the facial expressions and the body gesture and where people are in order to come to a conclusion about the perceived emotion of the group. So if I play this video again, you will notice that on the top right, it is showing the emotion. So perceived emotion is negative, and then it is also showing the intensity as well. This is essentially the valence axis. And what we want to do is, not just look at images, but if audio is also available, use it as one of the complementary modality to process the perceived emotion. The second research problem was, well, we would like to use emotion, use the affect analysis in different problems. So here is one other work wherein we are interested in learning a large scale representation of faces We call this work Merlin. Essentially, here is an input video. We track the face, divide the face into tokens, non-overlapping blocks, and in parallel, we also predict the segmentation mask of the face. We use the segmentation mask along with the RGB data as a masking, similar to how you have your masked autoencoders, and then the representation which we learn, which is Z here, we further use it to train different downstream tasks such as emotion analysis, face analysis, deepfake detection, and even lip synchronization. So you see here on the right hand side, this is essentially lip synchronization, wherein given a video or a single image and a driving audio, we would like to generate the lip movement. So the third one, which I was saying is, well, the affect of the user. How can you have better human-human or human-machine interaction? So the first one here on the left is essentially a real person, which is the speaker, and a listener, which is a virtual avatar, their interaction. And for the real person as well, we have transferred their facial movement in the form of the shape parameters and the texture parameters, just the shape parameters on a 3D model. I'll play this video and then I'll discuss this.
I think I understand.
Yeah.
I think
So
I
this person is
understand.
speaking, the speaker.
Yeah, one thing my mom always taught me, because I wasn't raised by my dad, but she always taught me that they'll always be there. So that's important.
Yeah.
Because
So you see at the end when the speaker says, and that's important, the listener also has a reaction, a smile. So we are interested in creating these engaging reactions from avatars. It's sort of for the future, not so far away future, where when we are going to use the e-commerce websites, rather than just using a text chatbot, we are going to have these virtual avatars with whom we can easily interact. Now, the research question is, given say the reaction of the speaker, then what would be the most appropriate reaction of the avatar? Because that is highly going to influence the experience of the speaker and could directly affect the decisions which a speaker is going to make on, say, that e-commerce website. Now, the other aspect of the improving the user experience is through understanding where is a user fixating at during a particular task. So for this, we would like to predict the user eye gaze and answer the question that where is the user looking at on the screen. And further, we could go a next level and say, can we predict that if a person is paying attention? So here is an example where these two individuals are watching a video, and at the bottom we are plotting predicting essentially the engagement for them. I'll just quickly play this video, and then you'll see how it goes up and down.
Some supporting community.
So as they're watching this video, the engagement goes up and down. So this can be used as a tool for neuromarketing as well. But essentially, from the perspective of eye gaze, eyes are such a strong indicator of many higher level concepts, especially say when there is a conversation happening or dyadic interaction happening. Then we would like to use the user behavior through the eyes, essentially where they're looking and where are they fixating on. So this is the last one, the last example which I wanted to show you is again around eye gaze, wherein we wanted to predict where is the user looking inside a car dashboard. And the problem is, well, creating these large data sets where the gaze is labeled is non-trivial. It's a very time consuming and very monotonous task. So in this work, we use the speech. So essentially labels are put on the different parts of the console and a user gets in, he or she reads the labels in a pattern they feel like. And then with some speech processing and speech to text, we generated the labels for the regions where the users are fixating. And then, you could easily predict using a neural network now that you have a large data set, which is 100% automatically labeled and tell where a user is looking at. Now, from this, we got very curious about deepfakes. So it's essentially, we want to understand that how do users react to synthetic data. And this was the beginning of this line of research for us in 2019, 2018. So the first thing which we did was we performed a user study where we showed around 40 subjects videos from a Google fake dataset, which had real low quality fakes and high quality fakes. And the users had a stereo camera in front of them to tell where are they fixating, and also a EEG gear. Now, this is one of the findings which I wanted to share with you guys, is to show how users react to deepfakes. So on the top left is a real video, and the top right here is essentially a fake video. So hang on, there seems to be a question. Let me go to the chat and see. Okay, can you please tell me again how speech is used in gaze detection? Well, in our case, we wanted to create a data set which is labeled by gaze. Essentially, where is the user looking at? So during the dataset creation, we had different tags which are put on the console of the car, and the user was asked to read when they look at a particular tag anywhere, say on the left mirror or the top mirror or the speedometer. And then we would create the labels directly from it. So fully automatic node labeling. However, I did not mention one more work in the continuation of this, wherein the hypothesis was, well, say someone is speaking into a microphone, and then, let's say talking to a group of people and looking at the people as well. Now, their head movement is going to also have an effect on, their relative location from a stationary microphone. So in that case, the changes in the speech pattern could be very useful to at least guess that when the user is going away from the microphone, and that in other ways can be seen as, is the head pose frontal or non-frontal. So in that work, we use audio embedding along with the video embedding to predict eye gaze, but that's another work in this. I hope in context of the car one, use of speech is clear now. Okay, coming back. So I was talking about deepfakes. Top left is a real video. Top right is the fake video where manipulation is done to the face of this individual. Now, in the video, there are three people: the main actor, the person whose head we see, and then in the third person in the background as well. Okay. Now, the second row is essentially the fixations, which tells us where is the user looking at. In the case of the real video, we noticed that the users were mainly fixating on the actor's face, but they were also looking at the movement in the background. If you compare that with the fake video, we see that if the users are able to notice that something is odd with the face, they are mainly fixating on the face of the individual only, and they're not really checking out the scene. So the gaze essentially here is more explanatory, trying to figure out something, rather than more exploratory, which is more free. So inspired by this, we realized that, well, we could design a neural network which is based on this observation that if something is off, the user will notice. Now, how will the user notice in the case of an audio visual statement? Well, one could say that if there is manipulation across audio or video, the user will notice a disharmony between audio video, which is exhibited by, say, loss of lip sync, unnatural facial movement, lip movement, etc. And this is inspired from a very classical work by Professor Grimes and others from the University of Texas, where they were looking at the effect of change in the audio visual sync in advertisement. So they found, well, if the audio and video are not very well synced, the cognitive load on the user is higher, the memorability is low, which sort of makes link to what we are trying to say. Well, if either of audio or video is fake, then they should not belong to each other in terms of their feature embedding. Okay. Now, this is a pretty old work by now, 5 years old. wherein we proposed this 3D CNN based network. We said, well, here you have a video audio pair, you divide it into chunks, you select the face, you extract the MFCC features, and then what you essentially want to do is I want you to draw your focus here. You want to compute a contrastive loss across the embeddings for the video pipeline and the audio pipeline with the same assumption that if you're using a contrastive loss, then the real audio and real video should come closer as compared to an anchor versus a fake audio or a fake video. Okay. Now, during the inference time, we simply compute a distance between the embeddings of FC8 of the video and audio. If the distance is higher than a particular threshold, which is summed across the different pairs of audio video, we'll say it's a fake. Okay. A very macro glimpse of the one of the results. So the last column is this proposed method, and we compared that with a Siamese network work which came out in ECCV 2020 in parallel, and then two vision-based work. The data sets under consideration are essentially the DFDC, which is a very standard Facebook data set, and also the DFTM data set, which is a slightly smaller size data set, but still used in defect detection. Now, as you can see, the method performs reasonably well on both the data sets. But what really got our attention was that because in this case, we are dividing the audio visual chunks, video into chunks, we can do a far more fine-grained analysis. Okay, I'll show you that. So the first is, say, just a fake video to indicate the point that, if the video doesn't belong to the audio, then there would be a large dissimilarity between the embeddings. So let's play the video. This is a fake video which I'm going to play. In this case, the face is manipulated, movement essentially of President Obama, and the audio is that of a real person, but not of President Obama. It is someone who's trying to mimic him, okay?
We're entering an era in which our enemies can make it look like anyone is saying anything at any.
So here we see that the distance between the audio and video embedding is quite large, which indicates that it's a fake. If I was to compare this to a real video of the president, I'll just quickly play this.
Hi, everybody. And I thank.
You see that here the embedding is actually, distance is fairly less. So which indicates this is a real video. But the main thing is, well, we are dividing a video into chunks. So we said, well, if you think from the perspective of someone who really wants to spread misinformation to deepfakes, they would be using fake chunks and real chunks together, mixed deepfakes, because long-term high-quality generation is still an open problem in 2025. So if you have a long video you want to generate, you want to do manipulations, it does need artifacts. So what we did was very early experiments in this work. We mixed real and fake chunks. So in this video, which I'm going to show you, the starting and the last few chunks are real. In the middle, they are fake chunks. And you want to see how will the method work in this case. So here are real, as you can see the ground truth as well. When the fake video comes in, so the score essentially goes high. And can anyone confirm that if you can hear the audio as well when I play the video?
I'm a self-motivated type person, so I don't need anybody fighting me.
Okay, thank you. Now, what I wanted to draw your attention here was, see, now the moment we are in the fake data, do you notice the face of this individual? Because manipulation has been done here. How the color of the face, the redness is different, how the gaze is actually sort of odd. So these are very typical indicators of the artifacts which these softwares would leave. The moment now we see real data, and I pause this, see in this case, the color distribution looks very uniform across the face. But the moment you're in the fake chunk, you see there are these artifacts. See the weird gaze and all. These are giveaways that something is manipulated. Okay, so based on this, we channelize all our energy towards these mixed deepfakes. Okay, that when you do subtle manipulation, say manipulate only a small segment of a video, it changes the whole meaning. So first I will play a real video, and the subtitles are also there for your reference, and then I'll play a fake video, and I'll show you how subtle manipulation does so much damage to the main message in a video. So here is the real video first.
Patch Adams and Mrs. Doubtfire are two of my favorite movies, so I'm looking forward to seeing what Robin Williams has in store for us.
So the person says Patch Adams and Mrs. Doubtfire are two of my favorite movies. Okay, here's the fake video.
Patch Adams and Mrs. Doubtfire are two of my least favorite movies, so I'm looking forward to seeing what Robin Williams has in store for us.
All what we did was we changed most to least, most favorite movies to least favorite movies, and it changes the whole narrative. And these are so difficult to figure out from a naked eye because they are surrounded by the real high quality data. Further, we argue that this problem of defect detection is not just a binary class problem, but it's also a localization problem as well, similar to how you have object detection. So from now on, we are doing both detection and localization. That is, we would like to also predict that what are those timestamps where manipulation has occurred. So one of my excellent PhD students, Zishi, he started working on then creating first this data set, which we call the localized audio-visual defect data set, which would contain these kind of scenarios where subtle manipulations are performed, but yet they change the whole meaning of a statement. So say you have an input video, real video, where this person says, I love ice cream. And then based on the text, you compute the sentiment from this, which is positive and 0.67. And then if you change the word love to hate, that changes the whole sentiment. It takes it to the negative direction, right? Now, just give me a second. I wanted to make this quite a, yeah. Now, here is the dataset generation process. So we have a real video audio chunk. We run a speech to text API. In this case, it was the standard Whisper API. We do NLTK based text parsing and extract the verbs and nouns and adjectives. Now what we want to do is we want to change the word which will have the maximum change in the sentiment. So that's sort of my objective here. So the antonym here should maximize the change in this overall sentiment of the statement, right? Once you have found that antonym, what we do is for that only word, the word which is going to be the replacement word, we first use voice cloning method to generate the audio, and we do a post processing. Essentially, we would add the background noise which was there in the original audio, which we had earlier extracted, and then we, with the generated voice, just for that word antonym, we would generate the facial movement. Okay, so here you could have, let's say, a wave to lip or a diff lip type of network, and that would generate a face movement. Then what you do is you could have three simple scenarios. First is simply replacing, so these chunks are replaced with the generated audio and video. The second is you keep the video as it is, but you change the audio. And third is you change the video chunk, but have the audio as it is. Again, just to create doubt, right? So many times you would have come across this the recent news where someone will say, that this video which is getting viral is not fake. I don't think this video is real because, they're not so sure. Well, that is also one way to spread misinformation by creating doubt about a video. Could be doubt about a real video or doubt about a fake video. So once we have this dataset lab.df, this is one of the methods we proposed. So the first half is essentially what I've already shown you earlier, where you have the video and audio, you have contrastive loss across the video embedding and the audio embedding. What we add here is essentially a boundary loss. What that boundary loss does is, so we notice that the transition from real to fake and fake to real, that is sort of the giveaway for detectors to figure out if something is real or fake. So essentially we say, well, we are going to penalize the network during the training if it is not able to predict the boundary frames that as accurately as possible. So this boundary aware loss then would add a lot of efficiency to this network. Now, when we compare with the average precision, average recall, we saw that MDS is the method which I discussed earlier, the disharmony between audio and video features, and then three other methods which are essentially coming from the abnormal activity domain. We see that when you want to have precision at 0.95 or 0.75, the performance is really bad, which essentially means that localization is a very difficult problem. Okay, so we continued working on this, and then we wanted to even go even larger in terms of the data, so that we could at least answer this question that, well, if we have a very large data set, in a controlled number of manipulations with respect to the type of methods, can we actually do better in terms of the localization? And we also were cognizant of the fact that, we have to understand that what is our baseline in terms of human performance. So Rishi led this study where he had 30 participants who looked at 200 videos, and just for simplicity, each video just had one modification. And this is how the interface looks like. The first the participant says if the video is real or fake. If they say it's a fake, then they have to indicate the timestamps. Now, if I just compare the human performance, that is the participant performance with the different methods, here you see that the performance, accuracy is fairly low. But this is what is shocking. It's very difficult to localize for us. It's very difficult to pinpoint exactly where the changes are made, simply because, if you even watch the video slowly or listen to audio slowly, it would be difficult. Okay. So we started working on this large data set then, and we call it AV Deepfakes 1M. And then, the second version is called Deepfakes 1M++. Here, what it look like in the real video is actually Voxelib 2, LRS3, and engagement data sets. And the three data sets are chosen just to have some sort of variety in the real repository, because engagement is one of the data sets which we created for engagement prediction back in IIT Ropar, where we had very different sort of illuminations which we could add. Now, okay, the pipeline is very similar. We have the real and audio coming in. Now, for the manipulation, we thought, let's use a large language model. Let's use ChatGPT here. So audio video sample, which is real, we use Whisper, extract the text from the audio, and then we use this type of prompt where we say you are a helpful text modifier. Your target is to modify the provided text to invert its meaning to the opposite direction. Here is the transcript of the audio. Please use the provided operations to modify the transcript to change its meaning. The operation can be delete, insert, or replace. Earlier, all we were doing was replacement. Okay. Now we want to insert new words. We want to delete as well, which could change the perception of the statement. And this is how the word cloud looks like. On the left is essentially the old word cloud before the manipulations are performed in the text. And then you see the manipulations, after the manipulation, how the meanings of the most frequently occurring words have changed. Now, once the manipulation is done to the statement, we have these different audio models which are being used to generate the manipulation. Now, what we also do is using the existing phase, this is an open source meta denoiser. We extract the speech as well and the background noise. So we add the background noise to the generated fake speech. Now, hey, these methods are a combination of both text to speech models and voice cloning models. Okay. So we see that once we are able to once we are able to extract the right manipulation, then even if, let's say, for a voice cloning method, the output is not very close to the real subject, we noticed that the observers are not able to figure out that there's a manipulation. What does that mean? Say you're listening to an audio and all of a sudden, there's a fake chunk which is inserted or something was replaced, but the voice style doesn't really match 100% to that of the original speaker, but somewhat. It's like similar to, when you are streaming something on YouTube or on some other streaming website and the bandwidth goes down and there are some errors or packets which are manipulated. Now, from the different type of fake audios, we generate the talking face as well using different methods, talk clip, latent sync, and deflip. But what we also wanted to do was that, we wanted to make the head pose movement consistent. So what that would mean is, say when you are replacing a word and say the word which is being replaced is half a second long, and the new word is 1 second long. So it's quite, it's almost double in duration. So based on simply frequency sampling, we would use the face from the original word as the driving video so that the head pose change is maintained across the manipulated segment as well. Once that is done, then again, replacement, insertion, or deletion, three modifications across, again, audio visual change or audio only change or video only change in the real video. Further, we also wanted to have a lot of perturbations, a lot of changes to mimic the errors which can be there in the real world settings to the real data and the fake data both. So we did extensive experimentation over this data, okay? And for the past year or so, we have been running this benchmarking effort as well, along with colleagues at different universities, where about 100 or teams have been participating in the challenge, wherein they are trying to do both detection and localization on the AVD fake 1M plus plus dataset. So I'll just quickly share some of the learnings here. We found that when folks are using multimodality, that is actually, of course, more useful. The high performing models were using very strong backbones like Wave2, Vec2, intern video and TSN, etc. One of the very interesting papers this year that also tried to see how well the state of the art vision models can actually work on defects, detection defects, and well, they found that without fine tuning, they were not really useful, not very accurate, especially for the task of localization. Further, we see that there are a lot of these open sort of venues to move from here. One is, well, adding more language, changing ethnicity, etc. So the dataset needs to have a lot of variety, and even camera view as well. So if you see defects of today, they are mainly frontal, but non-frontal defects are even more difficult to detect for the naked eye. Further, we think that we have to, of course, have these large foundation models for face representation. In fact, there is this very cool work which has come from the IDEAP lab, where they have this face foundation model. We think those kind of models are really useful. The embedding from them for having a training a detector which could better generalize across different types of methods of manipulation. Now, as I was mentioning about culture and cross language, here is an example. So on the left is a real face, and on the right is a face swapped video. Now I'll just quickly play this.
We spoke Japanese at home, ate Japanese food, watched Japanese TV, and on Saturdays, my parents.
So essentially, this is face swapping. But when I looked at this video first time, I was quite confused. To me, they look like the same person, though there is a subtle difference. So along with colleagues at American University of Sharjah, we have been trying to understand the effect of language and culture on perception of defects. So what we found in our study was that users, when they are asked to predict within their own culture, can spot a deepfake with a high accuracy of 87%. But this accuracy goes down the moment they are shown data from other ethnicities. Say same language but different ethnicity, and the accuracy goes down because we have less prior knowledge, prior experience. But if we simply analyze the EEG data which these participants provided when they were looking at these videos, we see that even a simple classifier like a linear SVM is able to achieve close to 85%, which means that we can actually learn detectors which can be more robust to the aspects of ethnicity as compared to native eye. It also means that from a perspective of deepfakes, cross culture, cross language is very non-difficult. It's non-trivial for us to find out if something is manipulated. So the other thing is, that was across cultures. We also try to work across language. And, I come from the state of Punjab. So, typically in Punjab, we would, when we speak, we'll mix Punjabi and English and Punjabi and Hindi or Hindi and English, Hindi, English in our day-to-day communication. And it's not just limited to India where people will, mix their native language with English, but it's also very prevalent around the world. So for example, in the Arab region, where folks could speak different dialects of Arabic, they would still use English words and vice versa. So with his colleagues at the MBZ University of AI, we are curious about detection of deepfakes and localization of deepfakes, where code switching is happening. That is, the speaker is changing languages across languages as well. So here is this pipeline. This work is under review right now. You have these sort of real statements. The people may have originally spoke in Arabic and English or just Arabic English. Then we would use a fine-tuned version of Whisper, which works pretty well for Arabic language. And using JICE and other LLMs, we try to do the manipulation similar to AV defects 1M across the different word meaning, but we go one step ahead where we say, well, change the meaning, but try to insert the change with another language. So if it's in English originally, try to insert the change through Arabic language. If it's already Arabic, then try to insert a change or do a replacement with the English or with Arabic, but from a different dialect, because Arabic language also has multiple dialects based on the region where it is being spoken. So from this transcript manipulation, then the pipeline remains the same. You generate the audio, you generate the video, and that will give you a lot of these sort of samples where code switching is happening. Now, when we, of course, we did quite extensive study on the performance of current methods. Of course, localization is still a very, very open problem, especially in this code switching type of domain. Now, further, here's the question for you guys, okay? So here are 3 images. Can you please tell me which are fake and which are real? You could unmute or, you could type in the chat as well. Anyone? Which image is real? Which one is fake? Okay, middle is Sangeeta is saying middle, but middle is real or middle is fake? Okay, last one is real. Yogeshwaran says all are fake. Okay, middle one is real. Okay, great. So that's right. The middle one is actually real. The 2 on the side are fake. So with student Parul, who just finished her research work, as in finished her submitted thesis, we have been looking at subtle manipulations as well, wherein the underlying motivation is that if the manipulations are outside of the face and they're very subtle, they're very difficult to detect. So this work has been accepted in ACM Multimedia this year, and this is as follows. You take these rich set of real images from different data sets which are used for tasks such as facial expression prediction, human localization, or even task localization. And what we do is we will query a large language model and ask it for the manipulation suggestions that what changes should be made to this image such that, say, a fact which is about the main subject in the image changes on attributes such as clarity, emotion, values, etc., etc. And now, based on those manipulation suggestions, we would then do the editing using VLM itself. So we would generate the edit instruction and then we would do the manipulation in the image as well. And this is what it generates. So on the left is the original image. And then here you see the different type of manipulations at different levels. So on the original image, here is the person level change, then you scene level change where you see the first one first, the first person, the second person in the background was removed, the pose of the person is changed. Then in this case, the street signs, scenes are manipulated, person plus scene, street signs manipulated, person's pose is manipulated, object is added, person plus object, the cycle becomes a motorcycle. And then my favorite one, person plus object level change, where now you show the pedestrian also, sitting on the bike. So very subtle manipulations. But the point is that we need to generate this kind of data because we need to learn detectors for the real world. Okay. Now, from the same work, we have been extending it from the premises that, well, when you detect, you also need to tell to the user that what is manipulated. So essentially, the explainability aspect as well, wherein how do you tell to a user that the face, or say if it's a non-face image, what aspect is manipulated. So for example, over here, uh, this is the input image, and this what is blinking is the system telling that this is actually what is manipulated. Then you have a complex explanation from the system, and what our argument here is that this is too complex for non-technical users. So we should have more concise, simpler information which we can show to the users, say a 70-year-old person or a 10-year-old kid. So if the user clicks on view simplified explanation, this is the simple explanation which says, well, the yellow flower looks fake, and also generate these kind of cards. But then we also go one step ahead, wherein we say, how about I use the fake images on the left and the simpler explanation together to ping a VLM and ask it to generate what could have been in the original image. Of course, we can never be sure about what was originally there if we don't have the reference, but it sort of tries to make changes to the image based on what is fake in the image. And here is what you see in the sliding bar, showing that this flower goes away, but the intent is to have one more way or another visualization for the user to understand why something is a fake. And last, pretty old now, but a good demo nevertheless to show, is the same defect detector for the first work was integrated into a Zoom-based meeting one as well. This work is pretty old now, very relevant to the COVID times, wherein you could tell if someone is using a defect detection software. For example, here, and this tool, what it will do is it will take one person's face as an input one by one. And let's say, I'm speaking, I ask one of my students now, who's, well, she's no longer a student, she's a professor herself. So Professor Shreya then starts speaking here, and then the system will predict the possibility, the probability that this person is using a deepfake generation tool to impose on someone else. So this is a low probability. Then when we ask this gentleman who's using a close to real-time cheap fake generation tool, so the system says that there's a high possibility that this is a fake. So it's not just about the deepfake detection aspect, but it is also about how are we going to convey the information to the user. So in the explanation one, as we try to simplify the explanations, try to generate what could have been in the real image. That's another way, because we not just try to design methods, but we are also observant of the idea that at the end of the day, there is going to be a user who will be using this technology. So we have to think of ways on how the user will be interacting with the technology, and what are the most ideal ways in which we should be showing information. We should be presenting the information to the user. Guys, this is fresh off the oven. This is the last work which I'm going to discuss. Again, going beyond faces, this is essentially deepfakes are mainly limited to faces or scenes, but you could also have deepfakes which can be around the sign manipulation, right? So sign manipulated based deepfakes. So of course, there's a very bright side as well. If generative tools, as they are improving, we can generate these type of videos where we can show sign language based avatars. Very, I would say, very useful for users who use sign language. But then, along with generation, we also want to understand, what will happen if it's a fake sign language. Then, of course, it can be used for spreading misinformation. And one of our collaborators, who is a sign language expert, and he, when he looked at the data, he said, yes, the meaning of the data remains as intended. So that means even if there are artifacts around some of the parts, the major meaning is similar. So it is possible to spread misinformation through these kind of videos as well. Okay, so last slide. What we have found till now for deepfakes, that creation of deepfake detection and localization methods, that gains quite considerably based on what we learn from observers, reactions. Further, if I look at the first work, audio-visual dissonance is discriminative. It is discriminative only till the work is in one language, the data is in one language. The moment you present real data where there is a voiceover or translation which has happened, then the work would actually fail, because it will assume that there's always a lip sync issue, but lip sync can always be observed. Say when you're watching Netflix and you watch something which is non-English, but then use the English voiceovers, so lip sync observes. So the first network is always going to think it's a deepfake. Further, localization is something which is still an open problem, and it is a very important problem, as the quality of deepfake generation systems are going to improve, and people are, we have seen in the recent past that there are videos which are being circulated online which are mixed deepfakes, because they are difficult to figure out which are the fake components. Further, we see, well, more data the merrier. The AV deepfakes 1M plus has 2 million data points, 2 million videos. But the point to note here is that real data is equally important as fake data. So the manipulations within the real data to show the different type of perturbations which are possible in the real world, and also different environments in the real data, that's really important. Further, of course, for as I if I may generalize, for all vision problems, computer vision problems, strong features which are predicted are useful, and it would be very interesting to look at generalization-based approaches. Of course, it's non-trivial, but the pace at which the generative AI tools are progressing, that's amazing. The quality of videos and audio which are being generated, right? But what it means from defeat action this tool perspective is, well, either you retrain or you use federated learning sort of environment, but you would expect that some sort of generalizability aspect is there in the method as well. Further, most of the research towards faces, we need to have environment like group of people where manipulation happens, or even across modalities, So deepfakes in the medical imaging domain. So that's something also very relevant, because that can be used for insurance scams. The last is personalized model. So say tomorrow in my Samsung or Android or Apple phone, in the gallery app, there is a deepfake detection tool. Okay, it simply would tag images or videos for them being manipulated or completely AI generated. What would be very interesting is that as we use it more, the system should learn about the user in a privacy preserving fashion, and the model should personalize. Same goes for fake call detection as well, right? So the system should learn better how to figure out the real user's voice in different environments. For that, of course, in a very privacy preserving fashion, that type of uh, methods are going to be required. So yes, that brings me towards the end of my talk. Thank you so much for being the patient listeners, and happy to take suggestions and questions. I'll also go to the chat meanwhile to see if there are any questions. So there is a question: what if there is a problem of synchronization fake video with algorithm work? If there's this, yeah, exactly. Shweta, you got it right. That's what I was saying with respect to multilingual, voiceovers. The system will not really work well. So I'm talking about the first work. Of course, the current ones will work. And the question is, how were GPUs handled? Well, we had a who are collaborators. We had access to multi-GPU systems. So yeah, this is really data intensive. So thanks to Monash University and American University of Sharjah. Another question: which data set you have used for last paper? Sangeeta, last paper, are you referring to this work, Beyond Faces? If you can clarify, please. Oh, okay, Parul ACM. So, oh, well, there are different data sets in this. So, you see here on the left, PIC, emotic. So, this is person-centric, PISC, person-centric. So, these two are essentially used for localization of humans. So, person detection task, these are expression data sets. So, these are the real data sets which were used for having a lot of variability in the data. Okay, guys, any other questions, suggestions? Anyone?
So participants, you can write your queries in the chat box if you are having. So we can wait for 1 minute. Maybe they are typing.
Sure.
From Sangeeta Kumar. Thank you, sir. Okay. Sangeeta Kumar. Okay. I will do it. Okay, work. Yeah, I think so. There are no other queries.
G.
I would say. Okay, I think.
Okay.
Thank you very much, sir, for your insightful talk on deep analysis, especially current trends in deep analysis. So you have really explained well. I hope participants have at least got the idea that what kind of research is currently going on and what is the future in the field of deep fakes. So sir has given us a lot of different ideas that how deep fake is currently kind of detected. So thank you once again, sir. I, on behalf of my Department of Computer Science and Engineering and E and ICT Academy at MNIT, would like to thank you for accepting our request and delivering a wonderful talk on deep fake analysis.
Thank you so much, and thanks, Dr. Deepak, for the kind invitation. Thanks, everyone. Have a good evening then.
Thank you, sir. Our pleasure, sir.
Bye.
Bye. So participants will be having our next session at 5:10 sharp. That will be delivered by Dr. Badrinath Patro from Microsoft